For this assignment, you're going to need to have out a copy of your periodic table. First of all, we're going to go over some important definitions. An element is matter that's composed of only one type of atom. So the elements we can find on the periodic table: sodium, potassium, chlorine, bromine, iodine. Those are all elements, and that's the smallest piece of property that still retains the chemical and physical properties. Because even though we can break an element down into protons, neutrons, and electrons, and we can break protons, neutrons, and electrons down into quarks, protons, neutrons, and electrons don't have the same property as an atom does. Now, some of the elements that we see on the periodic table, they're all represented by what we call the chemical symbol. And for some of them, their chemical symbol is right along with their name. Aluminum is Al. Bromine is Br. But some of them, if you look at your periodic table, you'll notice gold is Au. Silver is Ag, sodium is Na, potassium is K. That's because the chemical symbols for these elements came from the Latin names of the elements. These are the older elements, the first ones that were found. Now, when we talk about an element, we talk about an element as the smallest piece of matter that still has the properties of the element. We call that an atom. An atom of an element, if it's broken down into protons, neutrons, and electrons, it doesn't have the properties of that element any longer. Take, for instance, sodium plus chlorine forms sodium chloride. Now, sodium is a silvery metal that's highly, highly explosive. Chlorine is a poisonous yellow-green gas. But yet, when we put these two together, their properties, their physical and their chemical properties change, and they form sodium chloride, which is common table salt. So, common table salt, which is a white crystalline substance, comes from this silver metal that's highly explosive and this yellow-green poisonous gas. Now, there's two places in the atom where we're going to find the particles, or the protons and neutrons and electrons. The nucleus is located at the center of the atom, and this is where the protons and the neutrons are found. The electron cloud is all the area that's outside of the nucleus, and that's where we find the electrons. Now, just to give you an idea, size-wise, the nucleus is so much smaller than the electron cloud, but all of the mass of the atom is in the nucleus. So that makes the nucleus very, very dense. As a comparison in your mind of the nucleus to the electron cloud, if you've ever gone to a football game and the size of the stadium that the football game was held in is the size of one electron, one atom, then the nucleus would be a little marble in the middle of the 50-yard line. So most of the atom is empty space. Very little of the atom is where the mass is. And so that makes the nucleus very, very dense. Now, the electrons, there are 7 different energy levels in an atom. And the different energy levels can hold different numbers of electrons. And that's because if you think about it, as we get further away from the nucleus, we have more space. So if this little dot is the nucleus, there's not much room in the first level as compared to what there would be in the 7th energy level. And so because of this, we can put more electrons in the 7th energy level. So in the first energy level, we can put 2 electrons. In the second energy level, we can put 8 electrons. In the third energy level, we can put 18. And then in the fourth through the seventh levels, they can hold 32 electrons. Now, there's an exception to this. The last energy level, no matter whether it's the first, second, third, fourth, fifth, sixth, or seventh, can only hold 8 electrons. And we call this last energy level the valence level. And you can never have more than 8 electrons in the valence level. So whatever is the last energy level, if the third energy level is the last one, there's space for 18, but you can't put more than 8 if it's the last energy level. If you look at your periodic table, you're going to see some of these numbers on the periodic table. You should have a chemical symbol written on your for each element. You should have a decimal number, which we call the atomic mass. And you should see a whole number, which we call the atomic number. So the things I've just written in red, you should see that on every periodic table. Now, what I'm about to write in blue, you may or may not see that on your particular periodic table. This top part, the -4 plus 2 plus 4, this is what's called the oxidation state. They may or may not be written on the periodic table. For most of the elements, and we're going to look at this when we talk about periodic table in the next lesson, but for most of the elements, you can tell what this is simply by its position on the periodic table. So it's not totally necessary to have those numbers on the periodic table. The other thing that you may or may not see is the electron configuration. And remember how I just said that you can have 2, 8, 18, and 32. The first energy level can have 2, the second level can have 8, the third level can have 18, and then the fourth through the seventh levels can have 32. What this is saying is that in a carbon atom, the first energy level has 2, and then the second energy level has 4. There's no other energy levels beyond that. And so this you can also tell just by looking at where the element is positioned on the periodic table. So you're not going to necessarily see that information on all periodic tables. The protons and the neutrons are what we call nucleons. Any subatomic particle that's being found within the nucleus is considered a nucleon. A nucleon are the protons and the neutrons. So the proton has a positive charge, the neutron has a neutral charge, and the electron has a negative charge. Now, when we get the mass of these particles, an atom itself is very tiny. So it would be almost impossible to mass a part of an atom. So what scientists came up with is called the atomic mass unit. They based the atomic mass unit on 1 proton or 1 neutron because they're very similar in size. So a proton or a neutron has a mass of 1 AMU. An electron is so tiny that it doesn't have a mass. Remember, we said about the protons and the neutrons being in the nucleus of the atom, and the nucleus is where all of the mass is located. The electrons are out in the electron cloud. They have a bigger space or a bigger area, but they have almost no mass. And so that's what makes the nucleus so very dense. The symbol for proton is a capital P with a plus as a superscript because it's a positively charged particle. The symbol for a neutron is a lowercase n with a 0 as a subscript because it's neutral. And the symbol for an electron is a lowercase e with a negative for a subscript. Now, how do we calculate these? Well, the number of protons is what gives an atom its identity. And the atomic number that you see on the periodic table is equal to the number of protons. So if you look for the atomic number, which is the whole number on your periodic table, then that's going to be the number of protons that it has. So look at sodium. Sodium, the whole number on the periodic table with sodium is 11. So sodium has 11 protons. To calculate how many neutrons we have, well, each neutron and each proton has a mass of 1 AMU, and that's what makes up the mass. So if we take the atomic mass and we subtract the atomic number, then that's going to give us the number of neutrons that's in that particular atom. So if we take the mass of sodium on the periodic table, which is 22.99, and we round it to a whole number, 23, if I subtract the atomic number of 11 from it, that's going to leave me with 12. And so sodium has 11 protons and 12 neutrons. Now, if the atom is neutral, and we'll talk later, for right now all of our atoms are going to be neutral, but if the atom is neutral, that means that it has to have a 0 overall charge. So if the protons are the positively charged particle and the electrons are the negatively charged particle, then to get an overall charge of 0, I would have to have an equal number of protons and electrons. So if the atom is neutral, then the atomic number is also equal to the number of electrons. And we're going to see cases where that's not so. But for right now, as we're starting off, that's always going to be the case. When we write a chemical symbol, this is going to be the symbol from the periodic table. And this number is going to be the atomic mass rounded to a whole number. If you're writing a nuclear symbol, then this is the symbol from the periodic table. And this is the atomic mass. And this is the atomic number. And remember, you can always get the atomic mass and the atomic number from a periodic table. If they give you enough information to calculate it, then use that information to calculate it and not the information from the periodic table. So, for instance, in this atom, chlorine 35. If we look at the periodic table, the whole number on the periodic table is 17. And so we would take the atomic number, and that gives us the number of protons. Now, the number of neutrons is the mass number, or the atomic mass, minus the atomic number. So 35 is our mass number. The atomic number is 17, so 35 minus 17 gives you 18. Right now, we said all of our atoms are going to be neutral, and so it would have an equal number of protons and electrons. So this would also be the atomic number. And then the next number is the nuclear charge. The nuclear charge is simply the number of protons and neutrons that you have in the atom. Sorry, the nuclear charge is going to be the charged particles in the nucleus. So it's going to be the number of protons. Okay, let's look at the next one. In example number 2, we're told that there are 15 protons and 16 neutrons. So if there are 15 protons, then it tells me that my atomic number is 15. And I can go and look at my periodic table, and I can see that element 15, or the element with the atomic number of 15, is phosphorus. So the symbol for phosphorus is P, and I know that I have 15 protons and 16 neutrons. So 15 plus 16 is 31. And so that's going to give me a mass number of 31. So my symbol would be P-31. Now, I have to have the same number of positives as I have negatives. So I have 15 positive particles, so I have 15 negative particles. The nuclear charge is the number of charged particles in the nucleus. The only particle in the nucleus that has a charge is the protons. Neutrons have no charge. So the nuclear charge is there are 15 charged particles in the nucleus. If I want to write the nuclear symbol, I'm going to put P, which is the symbol for phosphorus. I'm going to put the mass, or the atomic mass, at the very top, and then I'm going to put the atomic number at the bottom, which is 15. Now, for number 3, we're told that we have carbon 14. So our mass number is going to be 14. Carbon, we can look at the periodic table and see that from the periodic table, carbon has an atomic number. Remember, the atomic number is the whole number. So carbon has an atomic number of 6. So if it has an atomic number of 6, then that means it has 6 protons, and it also has 6 electrons. Now, the nuclear charge is that there are 6 particles in the nucleus that have a charge to them, so that would be the nuclear charge. If I'm going to write the nuclear symbol, I'm going to put the symbol for carbon, the mass, and then the atomic number. Work numbers 4, 5, and 6. Stop the video and then come back and check your answers. Okay, here are the answers to 4, 5, and 6. Check your answers, and if you have any questions, post them in the discussion board on the Schoology page. and I'll get back to you with an answer as soon as possible. Now, I want to make a few notes about this. If you look at number 5 and 6, you'll notice that argon and calcium in these cases have the same atomic mass. This is possible. Two elements can have the same atomic mass. Two elements cannot ever have the same atomic number. So they can have the same atomic mass, which is the decimal number on the periodic table, but they can't have the same atomic number, which is the whole number on the periodic table. Okay, a few more definitions. Neutral atoms. We talked about this already a little bit, but a neutral atom is an atom that has the same number of protons and electrons, and this gives the atom an overall charge of 0. So if I have sodium, sodium has 11 electrons, and we can tell this from the periodic table, because if we look at the periodic table and we look at sodium, the atomic number of sodium is 11. And so that gives it 11 electrons. Well, we said we can put 2 electrons in the first energy level. We can put 8 in the second energy level, and we can put up to 18 in the third. So the first energy level can hold 2 electrons. The second energy level can hold 8 electrons. The third energy level can hold 18 electrons. And the fourth through the 7th energy levels can hold 32 electrons. But whatever is the last, or the valence level, can never have more than 8 electrons. And that's really what atoms are trying to do. They're trying to make sure that their valence level has 8 electrons. And so that's how they become ions in this process to try to make their valence level have 8 electrons. They become charged ions. So if we look at sodium, sodium has 11 electrons. 2 can go in the first energy level, 8 in the second energy level, and then you've used up 10 of your electrons, so your last electron goes in the third energy level. Chlorine has 17 electrons, and we can get this by looking at chlorine on the periodic table. It has an atomic number of 17, and so 2 electrons go in the first energy level, 8 go in the second energy level, and then the last 7 go in the third energy level. Okay, we just talked about a neutral atom as being an atom that has the same number of positive particles or protons and negative particles or electrons. An ion is a charged atom. What all atoms are trying to do is they're trying to get 8 electrons in their outer or their valence level. And so they'll do this either by taking in electrons or giving away electrons. If we have an anion is a negatively charged atom, meaning that it has more electrons than protons. So for instance, chlorine. Chlorine, when it's neutral, has an overall charge of 0, and it has 7 electrons in its valence shell. It's going to do whatever it needs to do to get 8 electrons in its valence shell. There's 2 ways that this could be accomplished. We could either get rid of the 7 electrons, and then the second level would have 8, or we could take in 1 electron and give the third level 8. Now, it takes about the same amount of energy to give up an electron as it does to take in an electron. So atoms, for the most part, want to do whatever's going to use up as little energy as possible. So it's going to be a lot less energy for chlorine to take in 1 electron than it is to give up 7. And so when chlorine takes in 1 electron, now it has 18 electrons to its 17 protons, which gives it an overall charge of a -1. And so an anion is a particle that has a negative charge. A cation is a positively charged atom or ion. And cations have more protons than they have electrons. For sodium, its 11 electrons are going to be placed into the outer energy levels as 2 in the first energy level, 8 in the second energy level, and that last electron is going to go into the third energy level. This gives sodium 11 positive particles and 11 negative particles, or an overall charge of 0. It's going to do whatever takes the least amount of energy. And so it's going to take a lot less energy to get rid of that 1 electron in the third energy level than it is going to be to take in 7 electrons. So what you're going to have is that third energy level is going to give up its electron. And now sodium is only going to have 10 electrons. It's going to have 2 in its first level, 8 in its second level. So now it's got the 8 it needs in its valence level. When that happens, sodium only has 10 electrons, and it still has 11 protons, and that gives sodium an overall charge of positive 1. Okay, we're going to fill out these charts with the atomic number, the mass number, the number of protons, the number of electrons, and the number of neutrons in each of these atoms. We're also going to draw a Bohr model. We drew a Bohr model in the last exercise when we drew the atoms in this form, where we showed exactly how many electrons were in each of the outer shells. So this is a Bohr model. And we're going to draw those in this section also. So if we want to see for sodium, we're going to look at the periodic table, and we're going to see that sodium has an atomic number of 11 and an atomic mass of 22.9. So sodium's atomic number is 11, its atomic mass is 22.9, and the element is sodium. The atomic number is going to be the number of protons and neutrons and electrons, because these are going to be neutral. So I'm going to have 11 protons, 11 electrons. I'm going to round the atomic mass to a whole number. So 23 minus 11 is going to give me 12 neutrons. And my Bohr model, I'm going to draw the dot representing my nucleus. I have to place 11 electrons. So 2 are going to go in the first energy level, 8, and then the remaining electron in the last energy level. So let's go ahead and look at aluminum. First of all, look at the periodic table. Stop the video, look at the periodic table, and fill in the atomic number, the atomic symbol, and the atomic mass for aluminum. So from the periodic table, we can see that aluminum has a mass of 26.982 and an atomic number of 13. So we put the atomic number in, the atomic mass, and we would put in the name for aluminum. Now, stop the video and figure out how many protons, electrons, and neutrons are in aluminum. So the atomic number, which is 13, would be the number of protons and the number of electrons. We would round the mass number to a whole number, so 26.982 would round to 27, and we would take 27 minus 13, and that would give us 14 for our number of neutrons. Now, try to draw the Bohr model, stop the video, and then come back and check your answer. A neutral atom of aluminum has 13 electrons. So That would put 2 electrons in the first energy level, 8 in the second energy level, and that would leave us with 3 in the last energy level. What do you think the charge on aluminum would be for this atom? How many electrons does it want to get rid of or take in? Aluminum has 3 electrons in the outer shell, so it wants to get rid of 3 electrons. So its charge would be positive 3. Positive tells you it wants to get rid of electrons. And negative tells you it wants to take in electrons. And the number tells you how many. So right here, there's 3 electrons in this outer shell of aluminum. So that means to have a full outer shell, or have 8 in its outer shell, it needs to get rid of that shell. So it wants to get rid of, which gives it a plus charge, and it wants to get rid of 3 electrons. Okay, work the next one and then come back and check your answers. Looking at the periodic table, we would see that the element with the atomic number of 7 is nitrogen. And nitrogen has a mass of 14.007. So this means that a neutral atom of nitrogen would have 7 protons and 7 electrons. And then I would take 14, because I would round the mass to a whole number, subtract 7, and that would leave me with 7 neutrons. If I were going to draw the Bohr model, I'm going to represent the nucleus, 2 electrons in the first level, and then we'd have 5 electrons left. Now, it's going to be easier for nitrogen, or take less energy for nitrogen, to take in 3 electrons than it does to get rid of 5. So that would give nitrogen a negative charge because it wants to take in electrons. And how many does it want to take in? It wants to take in 3. So nitrogen would have a negative 3 charge. Go ahead and work the last 3 problems and then come back to the video and check your answers. Check your answers to these problems now, and if you have any questions, post them in the discussion board on Schoology, and I will answer your question as soon as possible. Answer practice questions 1 through 8, and then come back to the video and check your answers. Check your answers for this page, for these practice problems, and if you have any questions, leave me a note in the discussion board on Schoology. We already talked about ions, that ions were atoms of an element that had a different number of electrons. Well, now we're going to talk about isotopes. Isotopes are atoms of an element that have a different number of neutrons. And because they have a different number of neutrons, they're going to have a different mass number. So the mass number on an atom can change. The charge can change. The number of protons can never change. So if I have a different number of protons, then I have a different element. If I have a different number of electrons, I get an ion. And if I have a different number of neutrons, I get an isotope. The decimal number that you see on the periodic table is the average atomic mass of an atom. The reason that it's a decimal number is because it's not a whole average of each isotope. Every atom has isotopes, but it's not a straight average. It's what we call a weighted average between all of the isotopes and the abundance that you find them in nature. I'm going to give you an example of what is the difference between a straight average and a weighted average. Now, grades are an example of this. Have you ever had a teacher that grades you on a weighted average, which means that they count the test as a certain percentage of your overall grade? So we're going to say that tests are going to count 80% of our grade, and quizzes are going to count as 10% of our grade, and homework is going to account for 10% of our grade. So if we look at our grades and we have an 85 average for tests and we have 100% average for quizzes and 100% average for homeworks, let's look at how these grades are going to be different if we do a straight average versus a weighted average. If we do a straight average, we're going to take the three grades, 85, 100, and 100, and we're going to add them together and get 285, and we're going to divide that by 3. And so 285 divided by 3 would give you a 95% average. If we look at this as the weighted average, then you've got to take into account each of the percentages. So 80% of your grade, or 0.80, because to go from a percent to a decimal, we move the decimal point 2 places to the left. So 0.80 times the 85 is going to give you 68 points from your tests. 0.10 times 100 is going to give you 10 points from your quizzes. And 0.10 times 100 is going to give you 10 points from your homework. So this is going to give you an average of an 88. Now, on a straight average, you would have a 95A. On a weighted average, you would have an 85B. So there's a definite difference between a straight average and a weighted average. It's to your advantage for a teacher to grade you on a straight average as opposed to having them grade you on a weighted average. Because normally on a weighted average, your test grades are going to be the heaviest weighted item. So we're going to go back to calculating how many protons, neutrons, and electrons we have. So remember, when we have nuclear symbols, this is our mass number, and this is our atomic number. And our atomic number tells us how many protons and electrons. So they would all have 6 protons and 6 electrons. All 3 of these isotopes of carbon have a different number, a different mass number, because they have a different number of neutrons. So if I do 12 minus 6, that gives me 6 neutrons for carbon 12. 13 minus 6 gives me 7 neutrons for carbon 13. And 14 minus 6 gives me 8 neutrons for carbon 14. Okay, work the isotopes of uranium using your periodic table and figure out how many protons, neutrons, and electrons are in each isotope. Stop the video and do this, and then come back and check your answer. Check your answer here, and if you have any questions on this, post your questions in the discussion board on Schoology. Answer the 3 sample questions at the bottom of this page and then come back and check your answers. Sample question number 1 asks that 2 different isotopes of the same element must contain the same number of, and they'd have to contain the same number of protons. They can contain the same number of electrons, but with them adding the word must right here into the question, must means they only have to have the same number of protons. They don't have to have the same number of neutrons. As a matter of fact, if they're isotopes, they're not going to have the same number of neutrons. And they may or may not have the same number of electrons. Number 2, 2 different isotopes of the same element must contain a different number of, they have to contain a different number of neutrons. They can't have the different number of protons, and they may or may not have a different number of electrons. Remember, the number of electrons determines an ion, not an isotope. So isotopes of a given element are going to have the same atomic number. The atomic number tells you how many protons it has, and if you change the atomic number, you get a totally different element. But it's going to have a different mass number because it has a different number of neutrons. If you have any questions on any of these, post those questions in the discussion board on Schoology. Remember, we said the atomic mass, which is the decimal number on the periodic table, is the weighted average of an element's naturally occurring isotopes. So to calculate this, we're going to take the percent abundance of each isotope in decimal form, and we're going to multiply it by the mass of the isotope. Now remember, to make the percent abundance go from a percent to a decimal, you're going to move the decimal point over 2 places to the left. So chlorine has 2 naturally occurring isotopes. Chlorine 35 with an isotopic mass of 34.9689 AMUs, and chlorine 37 with an isotopic mass of 36.9659 AMUs. In the atmosphere, there's going to be 32.51% of chlorine, that's chlorine 37, and 67.49% of chlorine is chlorine 35. So, step 1, we want to multiply each mass of each separate isotope by its percent abundance. So, the actual mass of chlorine 37 is 36.9659 AMUs, and we're going to multiply that by 0.3251, and that's going to give us 12.02. Then we're going to take the second isotope, and we're going to multiply its atomic mass AMUs by its percent abundance, and we're going to get 23.60. We're going to take these 2% abundances, add them together, and this is the average atomic mass. And if you want to check yourself, we're getting that the average atomic mass for chlorine is 35.6. Well, we can look at the periodic table, and we can see that the average atomic mass for chlorine on the periodic table is 35.453. You should be very close to that number if your answer is correct. Okay, work example 2, and then come back and check your answers for it. Okay, check your answer to this problem and ask any questions on the discussion board that you need. Work practice problems 1 and 2, and then come back and check your answers. Check your answers now and ask any questions that you have on the discussion board.